So I know you've been anxiously awaiting this next video. So here we go, just another example problem. In this case, we've got 3 reactants. You can have as many or as few reactants as there are in the equation. So in this one, we've got 3, but sometimes you might have one with just 1. But the process is always the same. So remember, rate is equal to K times concentration of A to the N, B to the M, and in this case we've got C, and let's call it to the Q, just whatever. So again, we're going to look for, or just look through the data to find things where, in this case, 2 things are constant, 1 thing changes. Now notice here we're using pressures instead of molarity. Pressure is analogous to concentration because as the number of particles decrease, the pressure also decreases, so we can also use pressures for this. So here we've got, in the first trial, make it easy again, 1 atmosphere of each. In the second trial, we doubled actually the concentration of A from 1 to 2. B and C stayed the same. So doubling the concentration for A leads to what kind of change in the rate? And so when the concentration increases by a factor of 2, our rate stayed the same. We can say that increases by a factor of 1 if you want. And so, sorry, put my exponent in the wrong place. 2 to the N equals 1. So hopefully you remember from your math that anything raised to the 0 power equals 1. And so what this means is really A has no effect on the overall rate. It is a 0 order reactant, no effect. Keep going here. Between trials 2 and 3, A stays the same, C stays the same, and B has doubled. So for B, doubling my concentration leads to a 4-fold increase in rate. So 2 to the N equals 4. Sorry, that's M for B. So M is equal to 2. 2 squared equals 4. Makes sense so far, I hope. Now, for C, if I go back to, or I'll go to trial 4, I've got 1 and 1, which matches trial 1, and this time C was cut in half. So you can use 1/2 if you want to. I like to look at it this way. I'm going from 4 to 1 instead of 1 to 4, just because I like whole numbers better than fractions. So going from trial 4 to trial 1, I'm going to say that the concentration of C doubled. So concentration doubled, so 2 to the Q. Still going from 4 to 1, the rate doubled from 0.05 to 1. So 2 to what power equals 2? And of course, that's 1. So then I'm just going to put this together into a rate law. So rate equals K times concentration of A to the 0. And you can leave that out if you want to. We found out B is to the 2nd power and C is to the 1st power. Now, in the last video, I don't think we talked about overall order. For this reaction, the overall order is 3rd. It's really easy to figure that out. You just add up your orders. So 0 plus 2 plus 1 gives you 3. So that's a 3rd order overall reaction. Same thing for this one. 1 plus 2 is 3. So 3rd order. Again, adding your exponents. Nothing hard about that. Now notice with this one, I've got a 5th trial, and I've got a question mark there for the rate. So I can figure that out using my rate law. That's where this comes in handy. So the first thing I need to do, though, is figure out what my K is. So I'm going to choose any trial that I want to, doesn't matter. If you've got numbers that aren't perfectly, doubled and quadrupled, whatever, then you might want to look at more than one set of data and take an average. But I'm giving you nice clean data here, so we can just look at any one that we want to. So I don't know, let's look at trial 3. So the rate for trial 3 is 0.4 atmospheres per second. So we can just plug it into this equation. Looking for K. A, again, I can leave that out because it's something to the 0 power, which just means I'm multiplying by 1. Concentration of B was 2 atmospheres. And that's squared. The concentration of C in that trial was 1 atmosphere. It's to the first power. And so 0.4, I guess I have to use a calculator for this. 0.4 divided by 2 squared is 4 times 1 is 0.100. So that's your value for K. Now your units for K here, I didn't leave myself quite enough space. So when I solve this, I have units of atmospheres per second over atmospheres squared times atmospheres, which is atmospheres to the third. So it's similar to the molarity. That cancels to make that a 2. So I've got, really it's 1 over atmospheres squared times seconds. We usually write it as the concentration to the negative. And you could write seconds to the -1 also. Or you can put it over seconds, whatever you want to do. But atmospheres to the -2, seconds to the -1. So once you get to that point, then again, it's just plugging back into this original equation to find the rate. So this time I'm looking for the rate. Rate equals, now I know my K, 0.100 atmospheres to the -2, seconds to the -1, times B squared. So concentration of B is 0.5 atmospheres squared times C to the first, which is 7. So math's even easier here, just multiply. 0.1 times 0.5 squared times 7, and you get 0.175. Now notice what happens here with the units. That's why we have to choose our units for K. Atmospheres squared cancels out atmospheres to the -2. So the units I'm left with are atmospheres over seconds, which is a unit for rate, concentration over time. And so that's all there is to it. Once you get your orders, it's just a matter of plugging into an equation and solving for what you're looking for. So guys, I hope that was helpful to you as you work these problems. There's a little worksheet for you posted. Use your textbook for this. This is chapter 13. There are practice questions at the end of that. We'll probably end up looking at a few of those as we work through this. But see how you do with that worksheet, and we will talk soon.